in just here. And there was sort of a few curiosities in this measurement. Gamma ray spectrum itself looks very nice, but there's a few things I've marked with a question mark. And what these are, I think, are some collective states in contamination that happens to be radioactive contamination in the mass 110 beam. So it's not just ruthenium-110 that comes out of the CARIBU source. You also have other unstable mass 110. You know, the bending power of the separating power of the magnet is not sufficient to extract to separate all of those. So in something like technetium-110 or rhodium-110, there's some collective state or isomer or something that's also excited, giving rise to these two lines just here. Now, why this puzzled us so much is that we also took this very large amount of decay data. So this is looking at the decay of the radioactive beam inside Gratina with the aim of measuring branching ratios and mixing ratios. And these two lines happen not to be present in this decay data. So it's stuff that's only populated in Coulomb-excitation, is completely unknown to the nuclear database. Now, I mentioned with this EBIS source that this should give us access to backscattering data, you know, where we don't have this coincidence between the left and right hemispheres due to the cleaner beam. But actually, unfortunately, in this experiment, that couldn't be done because it was found that the backward windows of the PPAC detector were contaminated with californium. So even applying some time gate between the EBIS, you still weren't able to use this information. But it's not so critical, really. You see, even only measuring up to 90 degrees in the lab, you still cover center of mass angles of the greater than 100 degrees, up to 120 degrees in the center of mass. So you're really sensitive to these second order effects, the reorientation effect, etc. So as I mentioned, decay data was taken. And this is, I think, one real lesson we learned on this experiment, that when you're doing these Coulomb studies, it really helps to have complementary decay data as well. This is a very simple setup. It's just implanting the cocktail beam onto a gold foil in the center of Gratina. There's no active stopper or anything. It's helped by having excellent angular coverage in Gratina, and the aim really was to measure precise branching ratios to use in the Gaussian analysis, and if possible, but it's much more difficult, to measure E2-M1 mixing ratios. As in our previous analysis, we assume that everything is E2, which, although we suspect is the case, needn't necessarily be true. So this is just a snapshot of what we saw, and it's quite extraordinary, I think, that you see such a complicated level scheme built up from such a small amount of decay data. You know, the beam intensities are not enormous. Nevertheless, you can build up something of real complexity, I think. But what we're really interested in is being able to measure branching ratios for these low-lying states down here, and if possible, these E2-M1 mixing ratios, which I show here. So this is an example from our molybdenum 106 data. This is analysis performed both by myself, by Mitch Almond at Argonne, and also our PhD student Shaheen Jazravi. And the result for this molybdenum case is that we have a mixing ratio that's strongly consistent with about 95% E2 between these 2-to-2 transitions. So supporting our assumption in the initial analysis that these things were dominated by the E2 component. Okay, so what's the new information then from this study? Well, I flashed that up here. You saw in the gamma ray spectrum there were these two new gamma rays in ruthenium-110. So we can publish matrix elements for these levels. But as a result of this beta decay data, we also have these branching ratios. So for example, looking at this second 4+ state, we only measure this transition in Coulomb-X, but we measure these two in the beta decay. So being able to fix this transition and knowing these two branching ratios enables us to publish matrix elements for these states as well. So we've significantly expanded the set of matrix elements that we're able to present from this data. These were analyzed with the Gaussian code that was mentioned earlier. So very briefly, what Gaussian does is it's a chi-squared search code. So we provide our experimental gamma ray yields, as well as other spectroscopic data, such as the branching ratios we either get from the literature or we determine in our experiment, the lifetimes if they're known, as well as facets of the experiment, such as the gamma ray detection angles, modeling the stopping of the ions in the target, and we fit this to the experimental yields and find the set of matrix elements that best reproduces this data. And this I present just here. Now, the things to note here are that the matrix elements have improved precision over our earlier set of data, which is good, and they're also expanded. But a key result for us is that we have now quadrupole moments for both the first 2+ state and the second 2+ state. They have opposite sign, as one would expect. And as a result of that and our sensitivity to the signs, the interference between these matrix elements, we can also publish one of these controversial gamma values and beta values that were discussed earlier. I should add a note, I think, that the M1 matrix elements, so in principle, we can determine the mixing ratio from this from our decay data. In the case of this nucleus, that turned out not to be possible. And the reason for that was just some contaminant transition. But we were fortunate that previous work had been done in this Eldridge EPGA from 2018, so using Californium source inside gamma sphere, and they had been able to determine the mixing ratio, which happened to support our previous conclusions that it's completely dominated by this E2 component. So it's actually their mixing ratio we use in the analysis and not one we've determined ourselves. So what about the sum rules then that we've used to get these beta and gamma parameters? So briefly what they are, the Q² invariance related to this beta. So here you have to have knowledge of matrix elements connecting the ground state to 2+ states. And for this gamma value, which is the thing that hints at this triaxial deformation, we need to know a richer set of matrix elements. We need to know both the matrix elements connecting the ground state and 2+ states, as well as the matrix elements connecting 2+ states to other 2+ states. So I add a few comments on it just here. I mean, the natural question is, do we have enough matrix elements to determine these shape parameters reliably? I should say this is the central value, of course, of these matrix elements. I'll comment on the spread in these matrix elements in a second. This was demonstrated by Jack Henderson in this very recent paper in 2020, where I pinched this figure from just here. You get convergence quite rapidly. So in Jack's paper, he used a set of matrix elements determined, I think, with new shell X, and shown that this convergence for these central values was reached pretty rapidly. So although we don't observe a third 2+ state, in our data, we're just sort of linked. We just have this 0+ state and the first 2 2+ states. We don't expect this contribution from the third 2+ state to be significant. And indeed, that was shown by the Warsaw group experimentally. For this case of molybdenum 100, they were able to show that the contribution from the third 2+ state to this gamma value was pretty limited as well. So the question is then, what about the dispersion in this gamma? So as was discussed earlier, this is a much higher order invariant, so needs a massively greater set of matrix elements, which we clearly don't have experimentally. So the way we can attempt to address this is to perhaps use the theoretical matrix elements. So in Jack's paper, he made use of these matrix elements from new shell X. In our case, our theoretical matrix elements come from beyond mean field calculations. So we can attempt to do the same analysis with this set of matrix elements from the beyond mean field calculations and estimate it that way. These are also, I should say, very deformed nuclei, so there's perhaps a greater chance that these gamma values have more limited dispersion than in some of the cases presented earlier. And I just sort of flash this up as information, really. For a recent example where we've made use of quadrupole sum rules analysis in order to determine triaxial deformation. See this case of 130 xenon. This was analysis led by Lisa Morrison, who's a PhD student at the University of Surrey. This is a really nice paper that's using a contaminant from a higher Zolder beam. Xenon 130 is stable, and with this sort of short amount of data, we're able to determine these matrix elements, to support the triaxial deformation of 130 xenon. So these are results that we have both experimentally and are supported by shell model calculations, calculations with the Bohr Hamiltonian, as well as approaches with simple phenomenological models. I probably don't have time to discuss this in any detail, and since I'm not leading this analysis myself, I shouldn't say too much about it, but in addition to these ruthenium cases, we also have massively improved data for 104 and 106 molybdenum. And there's the nice case that you've measured two neighbouring even mass nuclei, so you can sort of tell a story between the two. So what about the outlook then? This is not a campaign of experiments that's finished. We hope that when things eventually get back to normal, fingers crossed, there's a chance that we'll run these experiments again next year. So these experiments will look at zirconium 100, hopefully ruthenium 112 should the yield be sufficient. Now this is a potential sign of both maximum triaxiality and oblate deformation, as well as this palladium case that Alison highlighted earlier. We've seen that the power of complementary data to support our Coulomb studies, and having this beta decay data massively improves your set of matrix elements, and we often find discrepancies with branching ratios and things in the literature that are difficult to reconcile with just Coulomb data. With these, we have the same as before. We have this access to backscattering data, hopefully, as long as we don't have more Chico contamination, with the possibility of determining these gamma parameters for these nuclei. I should just say further in the future, CARIBU will be no more eventually. They will not produce another CARIBU source. What they will do instead is a setup called new CARIBU. So this is neutron-induced fission of uranium. This, unfortunately, for those of us interested in these gamma soft nuclei, is not so useful as this shifts the mass yields. So instead of being focused on things like barium close to mass 140 and these mass 110 nuclei, you now shift it to closer to tin 132. So it's very useful for people interested in that. But there's some possibility of extracting refractory isotopes at facilities such as Isolde. So for the approach, as far as I understand, that they're taking is to try and produce molecules of these radioactive refractory isotopes that can be extracted from the isol target, then to break apart these molecules inside the EBIS, as is normally done with many beams, giving access to these sort of beams at facilities like Isolde. And I think that's all I would like to say. So thank you very much for your attention.
Thank you very much, Dan, for another beautiful talk at TASTE. You explain things so beautifully. So we have time for a question. Alfredo,
I got 8 questions.
I think it's an easy one. Oh. Alfredo Pova is asking about the errors in beta and gamma.
That's right, yeah.
Statistical errors, or?
That's correct. So they're just the errors from the statistical errors in our E2 matrix elements.
And I was thinking about M1s being populated in what kind of bombarding energies do you have? Do you have relativistic energies, or why do you have M1 contributions, you think?
No, so it's just the M1 bit is there. We only excite via E2, but you can decay via M1. Right. So some of the yield you're seeing could be from the decay of the M1 part of the decay. So you need to know this in your Gaussian bit.
Right. Okay, Dan, thank you so much for...
hang on, I've got some questions. Sorry.
Who has a question?
Hi,
Peter Butler. All right.
Thanks. Yes, very nice talk, Dan. Beautiful results, and congratulations on getting a value of gamma. Just to confirm, of course, as you alluded to in your talk, that you're measuring a mean value of gamma with an error bar, but you're not at this stage. I guess one needs more intensity from radioactive beams to go further the next moment to tell the difference between whether it's gamma soft or gamma rigid.
Exactly, yes.
Yeah.
I mean, the set of matrix elements is intimidating, I think, that one needs in order to do that.
Exactly, but something for FRIB maybe. The thing I mean, what I'd really like to highlight, this beautiful comparison you made between the two different types of charge breather,
between
the EBIS and the ECR. And I think that you know, that really does tell anybody who's building radioactive beam facilities in the future, or even in the present, that they really should throw away their ECR source. There's no doubt about that. You had these unidentified gamma transitions in the spectrum. Have you tried doing gamma analysis? I mean, you might think it's impossible, but
yeah, we have. So you mean sort of particle gamma? So
yeah, particle gamma.
Yeah. So the problem is that they're not in coincidence with each other. I think it's
in coincidence with anything else, though.
No, it looks like two collective states, and we can't even say what nucleus they're in.
Right. Okay. So it doesn't fit the 2+ or anything like that.
Yeah.
Oh, okay. All right. That's fine.
Probably, you know, if in a really well set up experiment, what one would have to do is investigate with things like you know, the EBIS settings or something at the time of the experiment, see how that changes the yields.
Yeah. Okay. All right. Thanks very much. Very nice. Thank you.
Yeah. Thank you, Peter. Cheers.
Any other questions? I don't want to miss anyone. Alfredo, you want to say something?
No, he has answered me. It's
excellent.
It's perfectly.
So,
I wanted just to know that I was. Well, this is a very long discussion, but one thing I wanted to ask you, just to put the things, what you measure is what you measure.
That's right.
This is the reality. Sometimes we have the problem of how to name that. In many cases, we need to have a semantics that is familiar to us, and this brings us sometimes too far into the semi-classical regime, because it's not very easy to give names to phenomena which are radically quantum, because we don't live there. We don't buy the bread in a quantum patisserie.
Okay, I think we're going to stop here because my DVC research is waiting. I don't want to have to wait for too long, otherwise I'm going to be in trouble. So we have the Women in Science next, but before, thank you so much, all the speakers, and again, beautiful talks by everyone.